Okay, so just on the record, everyone agreed to be recorded, right? Okay, so because
Yes.
I want to use this for future graduate students and undergraduate students, and then so I have to admit this this renormalization group calculation is not trivial at all, and then the interpretation. And then fortunately, because it's tricky, so I think people didn't get quite right. So that gave us the opportunity, because otherwise it would have been resolved a long time ago, right? So there wouldn't there would be no problem for us to work on as far as this particular problem is concerned. Okay, so I'm gonna start sharing a screen. So you can see my screen? Can you guys see my screen?
Yep.
Yeah.
Yep.
Yep.
Okay, so okay, so I'm gonna shrink this one. Okay, so I'm gonna start with the famous Jonah Ike thesis. Okay, from 2023. Okay, so so I so let's go to the part. So I think okay. So you understand the idea of renormalization group is the change in the scale when we rescale the system, and then we demanded the rescaled partition function is the same as the original partition function. So there is no as a matter of principle. So this is a demand, and then it's the assumption that our understanding of thermodynamics is only makes sense when n goes to infinity. So if we look at the original problem of n particles with the interactions with the Hamiltonian, we write down the partition function, and then we let n go to infinity, then that partition function would give us allows us to calculate the thermodynamic quantities. When we say thermodynamics, we mean the system size goes to infinity. So therefore, when we look at this, when we change the scale of the system, and then at the critical point, this shouldn't matter to the partition function because n is equal to infinity. So this is the basic idea behind the renormalization group. And then from your thesis, it's very clear, Jonah, you understood it. Okay, so that's the idea: is to change the change the partition, is to change the scale, so then to integrate out the smallest pairs of the domain walls. So this in this picture here, so when you integrate, when you change the scale for a to a times e to the delta L, okay, and then so with the understanding e to the delta L is actually 1 plus delta L, right? So that's the idea. So when you integrate over range, then you effectively get rid of these pairs. So then, and after you integrate this out in this big sum, okay, big integral here, then you effectively would change the coupling constant between the domain wall between these two domain walls. So that's the idea. Okay. So it's very clear you understood it. Okay, so you get it this correctly. Okay, so the first RG equation. So you everyone understand that this is the differential form of the RG equation. So by setting dk dl to 0, so this is called the beta function, right? So this quantity here is a beta function. So beta function here. So when 0, so then it will be a fixed point. So that you see k equal to 0 is a fixed point, y equal to 0 is a fixed point. So So when we do the plot, you will see y equal to 0 is a whole line, okay? And then k equal to 0 then is determined by this. K also equal to 0 is also a fixed point, but it's a k equal to 0 means t equal to infinity. Okay, so that's it's also a line. And when we draw the diagram, okay, actually we can draw it right here. So when you plot, so this is k, and then this is y, okay, fugacity, okay. So so from this equation here, so this is this quantity here is called the beta function, okay, the famous beta function. So by setting this guy equal to 0 is a fixed point, means the k is no longer scale dependent. Okay, so there are two situation where you can satisfy this one. One is y equals 0. So y equals 0. This is this whole line here. Okay. So this is a whole line is a fixed point. Okay. K equal to 0 is also a line here. Okay. So this is also a line here. Okay. So this is also a line, a fixed point. Okay. Okay. So but this is equal to t equal to infinity. So we know this is a disordered phase. Okay. So that's not that interesting. What's interesting is y equal to 0. Y equal to 0. Y is the fugacity is e to the negative the energy to create is the chemical potential. Okay, it's the free energy change by adding or subtracting, in this case, a domain wall. Okay, so y equals 0 means mu goes to infinity, means the energy cost to create a domain wall is infinite. If the energy cost is infinite, that means you cannot create it. So that means the system would be ordered, right? Would it be ordered? But obviously, so the first equation doesn't tell us the whole story. Okay, so then there's a second equation. The second equation for the fugacity is this one. But actually, if you do the algebra properly, okay, there's a subtle point here. Okay, I didn't quite appreciate it at the time. Okay, so if you go to Kosterlitz lecture, Kosterlitz lecture 2. Okay, so we go through the algebra. Okay, so other than typos here and there, there's no big mistake that you might note. Okay, it's this one here. If you do the Hamiltonian Mike defined, there's a factor of 1/2 here. Okay, so this is the 3 RG equation was derived out of the algebra. Okay, so this 1/2 here is there. Then what Mike did was, well, he said, since if I redefine k to be half of k, then so if half a k is new k, then this one has no change because I have k both sides. So in fact, there's no difference. Okay, so this there's an interesting feature here. That means k, in fact, can have so k we know is k is j over kbt, right? So which means if you can define k arbitrarily that way, that means the cross TC in fact can be arbitrary. Do you notice? Okay. So in fact, the factor of 2 we were so obsessed about was why Mike said this is not important. And that's what he mean. but he never truly explained why it's not important, because RG equation by itself cannot define TC properly. Okay, so TC in RG is just a number, it's an arbitrary number. Okay, so in fact, this is where the Monte Carlo is really useful, because the Monte Carlo gives you the correct TC. So the way it's defined, then the so Jonah, when you find that your TC is twice of the Anderson-Yuval, both of you are right. It's just depends on how you define Hamiltonian. So if there's a factor of 1/2 in the original Hamiltonian, and then you will get Anderson-Yuval value. And if you didn't have that factor of 1/2, then you will get 1 point something like a 1.6. Okay.
So sorry, quick question. Sorry. So like in high energy theory, right? Normally in these situations, you fix your physics by using some physical scale,
Yes.
like the mass of the proton or whatever.
Yeah.
So in this case, is it essentially that we're missing that physical scale, because otherwise we would be able to get a specific TC, or is it more complicated than that?
That's a very good point. Okay, so okay, so the it's the critical coupling constant, right? So so what this RG equations tell us is the this critical coupling constant is just a arbitrary okay, very good point. The answer is yes. It is still decided by the coupling constant. Why? Because this, if you look at this, okay. So the okay. So then let me. This is where it's interesting and subtle. Okay. So to answer your question, what is the critical? So TC is determined by the coupling constant, right? So the coupling constant is defined in Hamiltonian. Okay, so let me see. Let me pull out the Anderson-Yuval as well. Let me see. So this is the famous Anderson-Yuval paper of 1971. Okay, so you can see why the people call this RG the Kosterlitz RG, because Anderson never really. So after this Anderson-Yuval paper, Yuval quit physics. He went into computer science. He's a big shot in machine learning, by the way. He's one of the pioneers in machine learning. He works for IBM somewhere. Anderson never bothered to explain this paper. So I guess people were so upset with with the frustration to read this paper, so they call it Kosterlitz RG. So there's a factor of half here. So okay, so if you consider this a factor of half here, then the TC. Okay, so this TC you get, okay, is this is this 0.79 here. Okay, so the way you get this TC is by setting C to be 0. Okay, by setting C to be 0, setting J to nearest neighbor to 0, you only consider the long range term. Okay, and then the fugacity you get is the fugacity. Sorry, no. You don't set C to 0. C is 0.577. C is the Euler constant, I believe. Let me see. Yeah, you can't set C to 0. C is, yeah. C is the Euler constant, okay? So what you get is the e to the negative 1.577. That's your fugacity, okay? So that gives you the, as we'll see, you get the TC, okay? So the answer is yes. The critical coupling, the TC is determined by coupling constant, but the coupling constant doesn't matter in terms of how you write down your Hamiltonian, right? Because you effectively change your coupling constant there. So by rewrite the K from the half a K, and then might effectively change the coupling constant by a factor of 2.
Okay, thanks.
Okay, so that's it. Okay, so so from your thesis here, what I can see, okay, so I have to admit I didn't when you write your thesis, when I'm reading your thesis, I myself did not fully understand this Anderson-Yuval-Kosterlitz RG. Okay. So this summer is really Owen, I was hoping that you will read the whole thing and then derive it and explain it how it works. And then when you told me this finite-size scaling doesn't work, and then before we can publish anything, then I decided, okay, I have to do. I have to chew through this, and then so it's good. So Owen, I have to thank you for forcing me to chew through this. Okay, so it's very clear that Jonah, from this 2RG equation, okay, from this 2RG equation, you went through the algebra here. You understood the algebra. Okay, that's very good. Okay, so. Owen, Abdullah, do you know how to get to this point? Can I get a confirmation from both of you? You understood how to do this algebra. This is just
I've done it before. Yeah.
Yes, you chewed me out in the past when I didn't know how to, and I went through that night and I.
okay. So
Yeah.
then okay. So the key point here is, okay, so starting from here. So this is where I think where Jonah did not truly appreciate the beauty of this. Okay. Well, I didn't appreciate either. Okay, so the is this guy here. Okay, so this is a really significant. Okay, so what this says is the following: is at let's get L log KL. Okay, okay, minus 2y squared. Okay, is at L is a constant, so which means is this one as well, right? Okay. Okay, so this is where I think most people get lost at this point. Okay, so I was lost. Okay, so this was in. Okay, so this was in Mike's 2016 review article. Okay, so it was here. Okay, so then he said the transition t is determined by equation 8 by setting this one to 0. Okay, so in other words, TC is determined by this one. Okay, but then how do you understand this? Okay, so then okay, so this is where I after chewing through, I really I understood it now. Okay, so the idea, so basically the idea is the following. So this equation here equal to 1, all this one give you. So this is where ChatGPT is really helpful. You can just force ChatGPT to plot it. Okay. So the if you plot this y, so ChatGPT do this kind of a work is extremely reliable and extremely useful. Okay. This is K. Okay. So the critical one is 1, right? The way we defined it. Okay. So then what you'll find is okay. So if C equal to 0, then if this is equal to 1, all you get is you get a 2 straight line here. Okay. You get this straight line. Okay, so what does this mean? Both, so both of this equation give you this. Okay. So because this is a fugacity, right? So K is 1 over temperature. So if you think about it, so on the right hand side is high temperature. Okay, so Y is e to the negative mu divided by KBT, right? KBT. So in fact, this is e to the mu. This is the minus, is essentially the e to the minus k, right? Well, okay, so it's, the mu is not j, so it's not k. So this is okay. So this is high, low t is high k. Okay, so when we go, when we change the temperature, then what happens is, this is high temperature, high K is low temperature. High K is low temperature. Okay. So when we raise in temperature, we're going to this red curve. Okay, we're going to this red curve. So what this RG equation says is exactly, so this is the point of Y naught. This is the initial fugacity. Okay, so then why is this one determines the TC? Because at this point, so this is where the tricky, why is so subtle. Okay, at this point, this entire line here okay, is the same temperature, okay? This line here is the same temperature. This whole line is the same temperature, okay? It's just the system is a fugacity versus K at this temperature at different scale. So what this says is at this temperature, if you look at a system at the infinite length scale, the Y is approaching 0. So the larger system size, okay, Y gets smaller and smaller. And then at the infinite system size, Y is 0. So that's the critical point. That's really the beauty of it. Okay, so I think, Jonah, this is the hardest part to appreciate this AYK-RG is why the TC is set by the bare coupling constant, bare fugacity.
So basically, at both, you can say that both in a Y versus K diagram, both J and T are changing. So you
No,
can have a line of fixed.
no, J is not changing.
So how is this? Sorry, I got confused. How is this a line of fixed T or a
This
different K?
No, this is a whole line. Oh, a very good point. Okay. So I see your point. Right. Okay. So okay, so on this red curve here, you agree. So this is the physics. So that if you so this is what they call a physical. Okay, this is a physical. This is a physical curve. What does it mean? Okay, in this every this means a different temperature. Okay, do you agree? So I'm changing temperature. I'm raising temperature. Okay, clear? Okay, so I guess well, this is where the confusion is. Okay, so along this red curve is where you're changing temperature of the system. So on that red curve, you can now say that every curve here you have a Y value, you have a K value. You can say that. But on this RG curve, then we have to think of this RG curve is what's changing is not temperature, it's the scale. So this is why there's an error on that. Okay, so there's an error, the error is pointing this way and the error is pointing that way. Okay. In fact, these two lines are from the same equation, they are from different temperature. Okay, so let me show you the okay, let me clean this up. you need. So I think this Jonah, I think this discussion will help you understand the RG in QCD as well. Okay, so you can see my PowerPoint here, right?
Yep.
Right. Okay, so first, let me go over the to make sure we understand where the C comes from. Okay, so this is from the okay, so let's first understand the algebra, then we discuss how we interpret this. Okay, so you understand how to go from by having this to this, right?
Yeah.
This is just a straight just algebra. Just this is where ChatGPT is very useful, and then basically allows me to use Wolfram for free, right? Because this you enter Wolfram, you get this one as well. So this is just a straight computation there. Okay, so there's nothing there. Okay, so now do you know then? Okay, so this gives you a TC, right? This gives you this is 1 over K naught, right?
Yeah.
You understand? Okay, so you understand K naught. Okay, so then so now if you allow the C to be finite, okay, to be a function of temperature, then you can see then this okay, so let me make sure you you know how to go from here to this equation. Do you know how to derive this one?
I mean, I forget slightly, but I remember doing this, so
Okay.
I have faith.
Okay. So what you do here is is you write 1 plus C over 2 is equal to a K over K minus log K, minus 2 Y naught square, So what you do is you write K as J over KBT, but a T, because little t is big T minus TC over TC, right? So then big T here, you can change it to J over KB TC, and then T plus 1, And then you treat this T as a small number, and you do a Taylor expansion, you'll get a C, So, so this is the algebra of this, of how you get this C thing, this C parameter, So this C decides how the RG flow curves look like, So, so you go to, so I'm plotting C, this formula, for different values of Y naught. So if Y naught is 0, is this black curve, then there's no negative region for C. C is always a positive, For so this 3 different color curves were generated just using ChatGPT, you can just plot it, right? So you plot y versus k, and with that parameter c. Okay, so you can just add it as whatever the parameter is, and if it's 0, you get it as 2 blue curves, and then if it's this is light blue, and then if c is positive, you get it as 2 deep blue curve. If c is negative, you get it this upper red curve. Okay, so then the question is, how do they? So this, remember, you cannot interpret this as different temperature. Okay, except you can say that it's a rescaled temperature. Okay, you can some people interpret that way. In fact, Bob Pekovitz like to call it rescaled temperature. But the way I like to think about it, the physical curve, the physical quantity we're changing. In fact, is so we're raising temperature. Basically, we're just raising temperature like this. Okay. So the fugacity, so this would be the fugacity as a function of temperature. Okay. So this is below Tc because so 1 over T is large, and then this is above Tc. Okay. So this is raising T. So the T goes up. So this is really physical. Okay. And then when it's crossing the blue curve, then you should then shake your head. Okay. So now I'm looking at it. So if I look at this here, okay, so now the system is at this temperature, okay, but at a different scale, the system have different properties in terms of fugacity. Hello? No, I'm in meeting right now. Sorry. About half an hour. Okay, bye. Okay, so what this says is at this temperature, if you look at the fugacity is 0 at the infinite. So which means the system, the larger the system you look at, it's the energy cost of created domain walk is bigger and bigger. So this, you can see it has a huge, basically decides the finite size scaling in the Monte Carlo data. So the larger you look at the system size, it costs more to create this domain wall, this topological defect. So therefore, fugacity gets smaller and smaller, and then finally, at the infinite system size, the fugacity is strictly 0. So the system is ordered. Okay, another way to say is, okay, so when the fugacity is 0, the energy cost to create the domain wall is infinite, so there is no domain wall at all. Okay, so the physics is governed by this fixed point. Okay, so you can see for every temperature there is a fixed point. So this is a line of fixed point. I think Professor Kosterlitz probably is the first person to call this a line of fixed point. So I think this is why people it's called this Kosterlitz RG, because even though mathematically it was first discovered by Anderson-Yuval, but Mike Kosterlitz was the first one to fully understand this, the beauty and the significance of it. And then later, this has a huge impact on the understanding 2D XY model, so it's more relevant to the superfluid helium, and then also 2D superconductors. Okay, so if you look at it, okay, so the fugacity for Anderson-Yuval model is 0.13, 0.13. Okay, it would be this blue curve here. Okay, would it be this blue curve? Oops, this is not blue. Okay, so what this says is the following. Okay, at Tc, okay, the little t equals 0. Remember, this Tc is determined by the bare fugacity. Okay, so this Tc is when it's 0. Okay. Well, when the little t is 0, c is 0. Okay. So when you raise temperature a little more, okay. So let's first think about T less than Tc, okay, because this is relevant to the magnetization rescaling, okay. T less than Tc then is this curve here, okay, this blue curve here, okay. So where C is positive, okay, C is positive, then you immediately, if you go plot it, you will see this one gets follow this. Yes. Okay, so C's follow this one. Okay, so but this curve and this curve is from the same equation. Why this corresponds to different temperature? Okay, so this is where you need to you need to look. Okay, so there are two regions where the C can be positive for this C parameter to be positive, okay? Y is below TC, okay? Y is TC, T is larger than the critical value. The critical value, if you remember in that formula, is 4y naught. So this parameter here, this one here, is 4y naught, okay? 4y naught. So that means, so this temperature here, where C becomes positive again, is where the is 0.4. Okay, if y naught is 0.1. Okay, so which means is when you raise the temperature, so you go from the so in terms of the curves, at a low temperature you have this curve, and then this curve get more and more straight, and then once it's at TC is straight, okay, here, and then infinitesimally below TC, you are on the red curve, okay, you are on this red curve, here. So what does it mean on this red curve? Is red curve, the RG flow is the first, is actually the fugacity goes down, but when you look at a system at a larger and larger system size, the fugacity goes to infinity. Okay, well, it goes to 1. Well, anything is large, then the RG breaks down. Okay. Okay, so then you get a little bit more. Okay, so you first, so you can see here. Okay, so there are, so for every point here corresponds to a line here. Okay, so you can see this bottom line here, the minimum value here is determined how big. Okay, so basically you can see this bottom of this red curve goes down. Okay, down means up here. Okay, so when C goes down, this goes up, right? Because it's determined by the square root of C. Okay, so when the magnitude of C gets big, more negative, and this one goes more up, okay? And then once it reaches bottom here, and then it comes back down, okay? It comes back down to the point where you reach this point. Once you reach this point here, then you get into the blue curve here on the left, okay? And then infinitesimally below or above this point here, then you start on the left-hand side. So during my sabbatical, I'm going to work with an undergraduate to make this a movie. Yeah. So this is where, you know, Mike probably was tired of having to explain what he meant for thousands of times. So he basically just said, "Well, you go figure out yourself," right? I tried to get him to explain to me how this works. You know, Mike was, "Oh, okay, figure out." Okay, finally I figured out. Okay, so really, I'm just really amazed how beautiful this is. Okay, so David Nelson was the first one to figure out, and then he immediately called this Kosterlitz RG. Then everyone called it Kosterlitz RG. Okay, but Mike now agreed that it should be called Anderson-Yuval RG. Okay, so we will call it AYK. And then so this would be more famous than SYK, right? Jonah, you know what the SYK is, right?
Yeah, I can't say I understand it well, but yes.
Okay. It's the associative Ye Kitaev, right? Okay. But AYK, okay, so this is the okay. So okay, so you understand how this flows now?
Yeah, that helped a lot.
Okay. So then okay, so this is how the RG works. Okay. How do you explain the this renormalization group flow? But then the question is, how do you go from here to the magnetization curve? Okay, so that's the issue, the front and center that we're dealing with. Okay, so that is from the okay. So and let me see your where's your thesis? Okay, so okay, you didn't write that down. Okay, so it's in the so okay, so it's here. Okay, so in order to understand the finite size effect of the magnetization, you need these three equations. Okay. So we just saw how the RG flow from these two equations tell you how the fugacity flows as the system fugacity flows as a function of system size change. Oh, not system size, a scale invariance. Okay, so this equation, this first two equation, the RG flow we just discussed, is for infinite system size, but it's at a critical point and how the fugacity changes as a function of length scale we look at. Okay, so then we said when we do the finite size scaling, we said this when we look at different length, and that length that's of relevance is the system size. Okay, so I want to make sure you understand the subtle difference. Okay. Okay, so the magnetization then is this one here. Okay, so you can tell. So, so first, if you think about just the how without complicated math, full integrations, we can understand why there is a change in the fugacity scaling behavior, the scaling behavior y versus L, because when k is less than 1, this coefficient is a plus. Okay, so then y would grow with L. When k is larger than 1, this is a minus, then y would shrink with the growing L, right? It's an exponential growth and you exponential decay. So that's a very easy to understand. Okay, so then if you look at this magnetization curve, you notice the coefficient here is a positive. Okay, so then you would say, well, for every fixed y, m can only grow with L. Okay, so this created tremendous confusion in me. I spent 2 weeks time, and Owen remember, Abdullah remember, I was struggling with this. And then because Mike was not very clear in terms of whether this RG works or not. I finally understood what he's saying. Okay. The RG,
Is this the sorry? Is this the absolute magnetization?
this is the okay. So excellent question. Okay. Oh my God, this is such a good question. So exactly what is this M? So to understand what this M is, we have to understand how it's derived from RG. Okay. So the way it's derived from RG is the M is the little m is the sum of the s of the spins coupled to the field. Okay, it's a uniform field in this case. Okay, so we'll you can see why I'm putting off the random field paper not as top priority for now is because we really need to understand the RG and the finite size scaling in the pure case. Okay, so so the way you derive this, you put this one in. Okay, so this m is still a local quantity. Okay. So then what you do is you do a size change A. Okay. This is the standard RG trick. Okay. Okay. And then you do this. Okay. So then you derive a mathematical form for M. So what does this M actually mean? So this M is because the way you did it was from the partition function. So now you look at this M at the larger and the larger length scale. So in fact, this M is the magnetization that you measure in your Monte Carlo. It's the sum of the spin divided by the number. Okay, so what this tells you is the how the thermodynamic magnetization changes as a function of the length scale, and then we make a jump in concept. Said when we do finite size scale in the Monte Carlo, we said, well, this is actually the system size. Okay, so okay, so we needed this equation. Okay, so then how do we actually solve this? Okay, so the way we solve this, okay, is so first okay, so first you can, it's a very simple exercise. This so you see here, so to prove that km square is the invariant, okay, means okay, so what you do is you said, well, I'm gonna take a, so this is if I type in a okay, so if I put a k over here, okay, so I'll get rid of this k here, right? Okay, I'll get rid of this m here by putting this m here. Okay, clear? I can do that, right? Okay, so then so if I do then I multiply by 2, so I have a 4 here, right? So then multiply 2 here. Okay, clear?
Yes.
Okay, so then I do a minus sign in the front here. Okay, so then I have 4y squared equals to 4y squared, right? So which means minus k dk dl, dk dl is equal to 2m dm dl, right? Okay, so this is so this is okay, so this is okay, so this is minus d log k dl. Okay, so I'm gonna move to the right is plus, okay, and then it's gonna be plus d dl 2 log m. Okay, so I can put this 2 inside, so this is m squared here. Okay, so this is equal to 0. Okay, so then this tells me then d dl log k plus log m log m squared is equal to 0. Right? So that means log km squared is a constant. So which means km squared is a constant at different scale. Okay, so this C is different from the C we just discussed. Okay, so this is why km squared is a constant of integration. So in fact, so this is so later actually David Nelson made a major contribution about this. So when you do the 2D XY model, and then this quantity equal to constant is the helicity modulus jump at the critical point, which is actually a universal constant. So this is and okay, so in our case here is the jump in the magnetization at the critical point. Okay, so just keep in mind at this point that this is a constant. Okay. Okay, so then okay, so if you agree this is a constant, okay, so okay, so can you guys see the my screen clearly?
Yeah, I can make out the
Yep.
the alpha. Yeah.
All the writing, right?
Yeah.
Because I don't want to make it let me see if I make it bigger. Okay. 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 So I rewrite K as a 1 plus X. So X is the deviation from 1. Okay. So this plot is then Y versus K is Y versus X from 0. Okay. So then we said that everything should be understood, okay, near the critical point. Okay, so we need to understand what this invariant quantity means. It means, remember, the one on the right hand side here and the one on the left side here are the same temperature. Okay, they're just at a different length scale. Okay, so then so that RG flow diagram, when you plot it in XY plot, and then it's the same plot. Okay, it looks like this. Okay, it's the same. Okay, so if we rewrite this one here, then X naught here, remember this point here, this is where the when you change the temperature, okay, you change your C here, okay? And this gives you the X naught, okay? Remember what a C is. C is this guy here, okay? So then I'm gonna did I skip a step? Okay, I think I did skip a step. Okay, let me not skip this step because this is a very important. Okay, to get because let me give you the punchline here. Okay, for this derivation, basically this guy here. Okay, this is K at this temperature at the infinity. Okay, this is at the infinite length scale. At this temperature, okay? At this temperature, okay? And then this one is KL at the same temperature. So that's why, okay, so this is what this guy says, okay? So you see K ML square is at K infinity T times M infinity. Okay, but why is that M at infinity is equal to 1? Because the fugacity flows to 0. Fugacity flows to 0 means when you have 0 fugacity, you have infinite energy cost to create the domain wall. So therefore, the system does not have a domain wall. So that the magnetization must be 1. Okay, so this is why it's the case. Okay, but there's an algebra in here. It's actually exact. Okay, so this is why I wanted to go over this. Okay, so this algebra is contained in. Okay, so you did not contain in the paper, but it's in the files we prepared. Okay, at some point we need to create a costless digital library at Brown to store all this different pieces of materials together. Okay, Mike is still young and healthy and kicking, so you know, we want to make a full advantage of it, take full advantage of
You
it.
can probably train a language model off of Mike while he's still in all this material, Sean.
I don't know. Well, when I started this summer, beginning of the, I tried to use ChatGPT to get a correct answer. It gave me all the wrong physics. But then when I figured out, I just use ChatGPT for simple mathematics, and then it really worked. And then gradually, now finally get the correct picture. Okay.
That's a good idea. We should make an artificial mic that we can just keep around forever.
Really?
Yeah,
Okay.
no, that's what we're talking about, yeah.
Okay. So this is what I'm talking about. Huh? Okay, so okay, so remember X is K minus 1, right? Because K is 1 plus X, right? Okay, so dx dl is dk dl, okay? Is equal minus 4y squared, okay? It's equal to c minus x squared. Why is that the case? Okay, it's because of this. Okay, it's remember. Okay, so this is a dk dl. Okay, this is dy dl, right? So this is k minus 1. Remember? X. Okay, so this is the same the first two RG equations we discussed. This is what we discussed so if you write it this as K, okay, and then this is K naught, then it's gonna be 1 plus C 1 plus C over T, okay. But once you expand it like this, is this, okay. So you need to do a little bit of algebra on this. But this is, you can see why it's the case. Okay. Okay, so what it means is, when we can use this y when we do finite size scaling. In order to calculate this y, we can just move this guy to the right hand side and move to c minus c here and take a square root and divide it by 4. Okay, divided by 4. Okay, so it's this. Okay, so which means it's 4y squared is c minus x squared. Okay, so that means then we can do a just simple integration of this. There's no approximation in this. Okay, and x naught is the initial value of the fugacity unscaled, and x not fugacity, the coupling constant. Okay, and then x is the rescaled one. Okay, so you do this integration. Okay, you get how the x scales with L, y scales with L. This entire derivation has no approximation. Clear? Okay, so then I'm switching back to the PowerPoint. So I'm just now copying what might give us the A and the XL. Okay, and then this looks like this. Okay, now I'll plug x in here. Okay, so you could put this entire thing in there, and then you needed to then ChatGPT can do the Taylor expansion for you. But I was afraid that ChatGPT might have fooled me, so I said, I'm going to do a brute force calculation myself. Okay, then I'm gonna, as L gets bigger, then it's safe to drop out of this term here. Okay, so once I drop out this term, there's a plus here. Okay, and then going from here to here is so from here, so basically I just put this x into here. Okay, so now it's here. And then all I'm gonna do, okay, so first I divided it by to make it simpler, but again neater. Okay, and then I turn L into log L as we do the standard. Okay, so make sure we are on the same page here. Okay, so remember when we do the rescaling, okay, is e to the L, right? So this is what we did. Okay, so when we change the scale, so this guy is 1 plus L, right? So this is why we this is where we do the rescaling. Okay, so this L should be interpreted as a log L. Okay, as we make the system size bigger, and then the rest is just straightforward algebra. Okay. Okay, to this term. Okay, so then you can see this when L goes to infinity. Okay, so if you do a Taylor expansion, that's fine. Okay, then it's going to be 1 minus this guy here. Okay, so you can see because of this, when you do this Taylor expansion, it's 1 minus A. A is positive. Okay, C over 1 plus square root of C L to the minus 2 square root of C. Okay. Okay, you see, so the whole thing hinges on the sign here. Okay, so if you do the similar scaling argument for 2D Ising model, you will find that this is a plus sign. So this is why in finite size scaling for a 2D Ising model, so the magnetization always gets smaller with system size, whether it's below or above TC. Okay, I suspect the graduate student or undergraduate student working with Professor Lewitton must have done something in her his or her, I actually don't know the gender of the person. and then they did something to their simulation to make it consistent with a 2D Ising model type of scaling behavior. But I think that missed the essential physics. The essential physics is when L goes to infinity, this guy is a constant. So this is the essence of the Thaller's prediction in this model, that the magnetization cannot change continuously to 0 at TC. It has to be discontinuous. So this is why they call it, this is a Thaller's effect. Okay. And the same goes for in 2D XY model and then the 2D superconductor. So this is why the IV curve, this is always, you wouldn't believe how beautiful it is when you actually do the measurement. I mean, you literally take at the time I use XY recorder, right? I can see literally at TC's voltage is current to the third power. A little bit above that TC becomes ohmic. That exponent changes from 3 to 1 in just tiny. I try to change the temperature. It's really discontinuous, as far as you can do experimentally. Okay. Okay. So then it also has an interesting behavior. When L goes to 0, this magnetization goes to 0. But what does it mean? It means that's exactly what it means. The magnetization does go to 0 if the system size goes to 0. If you only have one spin, the system cannot sustain equilibrium magnetization. So the RG really gives you the correct physics. Okay, so above TC, then the RG give you the correlation length, but it cannot give you the magnetization. So then that you require central limit theorem, as I discussed yesterday. Clear? So
Yeah.
Jonah, I want to congratulate you for being totally honest, that you put something in your thesis that was completely unmassaged, and then it finally made me realize, oh my God, it's in this case it's a thesis. And I pull out again, I said, wow, this is really a crossing point. And so then I told Owen, said, I'm sorry, then you have to give back the first authorship to Jonah, because in physics, whoever discovered, this is the most important effect. And then, so I want to thank that student in that Lewton's paper that made a mistake that gave us the opportunity to settle this. I'm pretty sure this is correct. And then, but nevertheless, Abdullah, I want you to do you was whatever get it, whatever get it. But
Yeah.
I believe you was on give the wrong physics. Because effectively made the system coupling even stronger. Okay, the periodic boundary already overestimated the interaction, but the Iwasan made it even more. So this probably will be itself another paper why Iwasan doesn't give you somehow hide the crossing. The crossing must exist.
Yeah. Okay.
But so now when you specifically refer to the crossing, do you mean the crossing of where magnetization
Versus temperature, different system size, yeah.
so it's basically how the magnetization is changing at different system sizes
Yes.
for finite systems.
Yeah.
So okay.
So basically it's this. So remember, this is what Lillian, Hawker, is that a boy's name or a woman's name?
I have no idea.
I can look this person up right now. Give me 1 second. Let's see.
Okay. It's a Messinfeld, unless you know how to pronounce German, spell German. Hawker Messen. So that beta is 2s, according to Stefan.
Give me 1 second. Hold on, my internet's a bit slow. Oh boy, come on.
But you see, the crossing should be like this. And then you can see the crossing point is a little bit above. So I think as you make this L bigger and bigger, that will be exactly that. You just have to admire this Mike's insight. Oh my God. He said he figured all this out when he was hanging on the rock, when he was doing rock climbing.
I think the guy's name. There are a lot of like German sports people who are guys whose name is Holger. So I don't know.
Holger is a guy's name. Okay, so it's a guy then. Okay, so what are they implying? What are they implying is this RG is a magnetization jump here, okay, and then you will go like this. This is what they're implying. Okay.
So we should see the same thing ultimately for regardless of periodic boundary conditions.
Ultimately,
The same crossing.
ultimately, okay, so ultimately is this. Ultimately, the magnetization jumps here. And then like this. That's what a RG predicts. So the effect of this, so the magnetization grows with system size is extremely slow, right? It's logarithmic, right? It's not logarithmic. This point is logarithmic. This point is logarithmic. This part goes as 1 over L to square times square root of C. So in other words, the further away from TC, and there will be less effect, right? So in fact, there's only finite a little bit of a window here, you can see it. And then that's exactly what happened. So I believe this is a very important result. And it's a I'm glad that so Mike is very important in this, right? Mike is just a brutally honest guy. When he doesn't know, he doesn't know, right? So when I first asked him how the magnetization should scale, he said, well, he doesn't, and he haven't thought about it. And then I brought up your data. I said there's a crossing, and then he thought of it. He said, "Oh, this crossing might be possible." And then now it's after finish the algebra, it's pretty clear. It's true. And then Professor Jen Topolchnik just wrote to me yesterday that he had gone through my algebra. He confirmed my algebra.
Mm-hmm.
Okay, so I'm pretty confident now. I'm gonna just crank up this paper. So Abdullah, if you can finish this Yuval exercise, run, say, do the same thing for 80 and 100, right?
Mhm.
And then to see if the crossing disappear or not, right?
Yeah, I understand. Yeah.
Sorry, what is the word you keep saying? Ewall sum?
Yuval is the image charge. Just adding more and more terms.
Oh, Ewall. Okay.
Ewald, the Nobel laureate. Do you know Ewald construction?
No.
Ewald diffraction. Okay, so if you take it, okay, if you take a periodic gradient, okay, if you take a point laser on it and then reflect on the wall, you'll see a diffraction pattern. That's called Ewald diffraction. Ewald was a German physicist.
Right, Ewald. I know now. Sorry.
Ewald construction. Yeah, Ewald is a after the war, Einstein. There was a story about Einstein when people ask, he met people from Germany, he said, "How's Professor Ewald?" But he never greeted it, said, "How's Professor Planck?" Okay, the reason is even though Planck was anti-Nazi, okay, but he didn't do as much as Ewald did for the Jews in Germany. So the Ewald was one of the German physicists really put his prestige and in fact his life for protecting many of the Jewish colleagues in Germany. So Ewald, Einstein had a very high regard for Ewald. And then Planck, Planck's son tried to assassinate Hitler and got a hand or got shot. But anyway, Planck was kind of a complacent, and he didn't stand up to the Nazi regime, and Ewald was one who actually did. At the time, Ewald was a Nobel laureate, Planck was a Nobel laureate, but Ewald is a very important physicist in Germany. There's a famous photo of 100-some physicists Soviet conference with Einstein sitting in the middle. Do you guys remember that picture with Madame Curie? Ewald was in that picture. You can look it up.
Nice, I didn't know that.
You didn't know that picture?
No, I know the picture, but I didn't know all this about Ewald. But that's really cool.
Okay. All right. Okay. So I hope you understand it now, right?
Yeah, I understand it a lot better.
Okay.
Can I just ask? So on a practical level, so what still needs to be done? And are there any ways that you want me to help, or at this point, is it better to just leave it in your guys' hands?
I think this one at this point we're all set. I think we have all the data needed. Unless you can figure out how to do a 10,000 spin simulation or a million, then I think we just have to settle with this system size. Because whether there's a quasar or not can be answered with small system size. So that's not going to be an issue. Refugees are not going to challenge us on that. So this paper will be the algebra of the renormalization calculation, and then the numerics.
Okay, and you're writing everything up?
Yeah, I will write everything up, and it should be ready. I will try to get it done next week.
Okay, and when do you go to Argentina?
The flight is September 15th. So I want to get this paper in, and also the proposal in. So I need to try to secure funding for Abdullah for his PhD thesis. Right now, we only have funding to sort of half of funding to get Owen finished by next May. Owen, I will be from February to the end of April. I will be in Taiwan. I will be back in the first week of May. You need to finish your thesis by first week of May. You need to defend, otherwise you won't graduate next year.
Okay.
So that's the timetable.
Okay.
And so did you, sorry,
In the
it's
meantime,
unrelated.
we'll have Zoom meetings. Yeah.
Sure. Okay. Thank you for letting me know ahead of time right now.
Yeah, okay.
So Sean, did you choose Argentina because of tango?
Well, that's a major reason, because the as a tango addict, and everyone says if you really understand the tango, you need to actually go dance tango in Argentina. And then what happened was really in the my life's work is the peak effect in high TC superconductors. I discovered. So if there's ever a Nobel Prize for that, I wanted to be part of it. But my biggest competitor in that was Professor Gabriela Pasquini, and she has a different interpretation for the same kind of measurement. So we actually did the exact same measurement. I did it first, but she repeated all my measurement, saw the same thing, but she interpreted differently. So then the question is whether I misunderstood her or she misunderstood me, and we need to settle. So I want to write a paper with her to settle this, because whichever committee decides, if the people still disagree on the interpretation on the basic simplest experimental factor, then they're not going to. This sort of, well, more research needs to be done.
Well, maybe your life's goal was always meant to be that, so that you could go to Argentina and have an excuse to tango.
That's so true, because the Argentine tango is really keeps me happy and healthy. Scientific work is very frustrating, right? Because you thought you understand something, and then you read another paper, so what you understand may be wrong, you miss something, right? So scientific work is frustrating. You need to keep a happy thought to continue. So tango keeps me happy. So, and at the same time, I can do the right kind of physics. So my trip in Taiwan would be it's 3 months, and that would be Professor Chafu Cho. He did his postdoc with Bob Austin at Princeton on nanobio. So I thought my second most important work is the nanopore DNA sequencing, which even John Hopfield himself thought it was very clever, but I had to stop because of the international politics, right? Because I was involved in the research in the U.S., the research in China. I was afraid I couldn't really disentangle myself from that, but now it's very clear that problem. No one has materialized experimentally yet. So I came up with the scheme to do it, but no one has demonstrated. So I want to see if I can convince my Taiwanese colleagues to do it, because they have the world's best nanofabrication capabilities. If anyone can do it, is the Taiwanese scientists, because they have the best nanofabrication machines and the capabilities. And then, so if I do it in China, I effectively have to help China to improve their nanofabrication at the expense of the United States. So that's a bit dangerous, right? Because I don't want Marco Rubio to be, calling me names,
You're always at risk.
No. I hope not. But Marco Rubio signed off my Fulbright fellowship, so scholarship. So I assume I'm on good terms on his book. Actually, the Fulbright this year got canceled for many people, and mine got approved by the State Department. So that's very nice.
Was this before the entire board resigned?
No. Oh, no. I was approved right before the board was resigned. Yes.
Okay. Interesting. Okay.
Yeah, but I think it has a lot to do with the fact that Argentina is a mega country, right? Their president said that they want to make Argentina great again. So I don't know. So anyway, so I'm just happy to do the kind of physics I want to do, and then there's the tango. They're trying to learn some real Argentine tango.
Very good.
I will be definitely doing weekly Zoom with both Owen Abdullah and probably Juan as well. We really need, we can't, you guys, This summer I've been on your tail a lot and pissing you off. I know how angry you are that I'm in the lab to check on you guys. I won't be checking on you, but you guys really, the ball's in your hand, okay? You need to get it done. This is your career we're talking about, okay? Okay, I'm gonna try to convince NSF to continue to fund us, but so we need to get this paper published, number one, and then get the preliminary data done. Okay.
Understood.
Yeah.
Well, thank you for meeting today to explain this. This helped a lot, and I'm glad that this paper is going to come out. And also, Abdullah, I don't even know if I can be helpful or not, but if you do want to discuss any of your coding or results, let me know.
Yeah, once they're done, I can discuss them, and then yeah.
Cool.
Okay.
All right.
Okay. All right.
Cool.
So I'm gonna stop recording now. I'm gonna stop recording. Okay.